You know, there are few drinks out there that just scream celebration quite like a glass of sparkling wine. And let's be honest, when it comes to bubbly, Prosecco is an absolute superstar. We're talking over 700 million bottles produced every single year. But behind that satisfying pop and all that fizz lies a really surprising story about energy, one that starts deep, deep inside the winemaking process itself.
You see, while we're all enjoying those crisp, fruity notes, there's a hidden and frankly super energy-intensive process at work. It's a part of the winemaking journey that's, well, a little less about romantic rolling vineyards and a lot more about industrial-scale refrigeration.
So that gets us to the big question for today. What is the hidden energy cost of that glass of bubbly? And maybe more importantly, does it really have to be that high? Today, we're uncorking a fascinating piece of research that found a surprisingly simple way to make Prosecco way more sustainable.
Okay, first things first, let's get a sense of the scale we're dealing with here. Winemaking, especially in Europe, is a major energy consumer. And I don't mean a few light bulbs in a cellar. We're talking about a serious industrial footprint. Look at that number, 1.75 billion kilowatt hours. That's the estimated electricity wineries across the European Union gobble up every year. And a huge slice of that pie goes to just one thing, refrigeration. Keeping things cold is one of the most energy-hungry parts of the whole operation.
So where is all that energy actually going? Well, for Prosecco, the answer is hidden in its very specific production method. Turns out the process used for something like 97% of Italian sparkling wine has a particularly frosty little secret.
This, in a nutshell, is the Martinotti-Charmat method. Instead of making bubbles in each individual bottle, the magic happens in these giant pressurized stainless steel tanks called autoclaves. It's super efficient for making large quantities, but I want you to pay really close attention to that last step, stabilization, because that's where things get really, really cold.
And right here, this is the energy culprit. As soon as those bubbles are formed, the wine gets plunged into a deep freeze. This timeline shows it's kept at temperatures below freezing for over 20 days straight. This whole time is dedicated to just one single chemical process.
And that process is called tartaric stabilization. Basically, it's all about forcing these tiny, totally harmless crystals called potassium bitartrate to drop out of the wine before it gets bottled. You know how you make rock candy? You chill a supersaturated sugar liquid to get the crystals to form? Well, for decades, the wine industry has done the same thing with just brute force, making the wine intensely cold for a very long time.
So, this massive energy drain from the big chill got some researchers thinking. They started to wonder if this long-held industry practice was actually necessary. So, they decided to challenge the conventional wisdom.
They asked a really simple but kind of profound question. Does it really have to be this cold for this long? I mean, when they looked into it, the EU regulations for Prosecco don't actually specify a storage temperature. This whole deep freeze thing is just an industry habit, not a legal requirement.
And this is where their solution comes in, and it's brilliant. Instead of relying on that brute force cold, there's another technique called the contact process. All you do is add a tiny amount of harmless, pre-made potassium bitartrate crystals to the wine. They act like little seeds, encouraging all the other crystals to form way faster. And here's the key, at much warmer temperatures, somewhere between 0 and 4 degrees Celsius.
Okay, so what does this actually mean in the real world? This small shift in chemistry, going from brute force cold to a smarter seeded crystallization, it has a massive impact on how much energy you need.
Just take a look at this. This chart shows the cooling energy needed to store the wine for those 20-plus days. The bar on the left, that's the standard deep freeze method. The bar on the right is the optimized process, storing the wine just a few degrees warmer. The difference is, well, it's staggering.
So, how staggering are we talking? Well, the research showed that just for the storage phase, this simple change can lead to a reduction in cooling energy of up to 100%. No, you heard that right. In some cases, especially for larger wineries, you can pretty much eliminate the need for refrigeration during that whole 3-week period.
But wait, there's more. The researchers found another key factor at play. It's not just about what temperature you store the wine at, it's also about what you're storing it in. The size of that autoclave tank makes a huge, huge difference.
And this chart shows that size effect perfectly. It's simple physics, really. Larger tanks have less surface area compared to their volume, so they lose their chill to the outside air much more slowly. As you can see, the energy needed for each hectoliter of wine plummets by almost 2/3 when you go from a small tank to a large one. When it comes to energy efficiency, bigger is definitely better. So, what's the big takeaway from all of this? Well, this research paints a really clear picture for a more sustainable future for our favorite sparkling wine. And the best part? It doesn't require reinventing the wheel.
So let's recap, shall we? The old school way of making Prosecco is a total energy hog because of that long, deep chill. But a smarter, science-backed technique lets wineries do the same job at warmer temperatures, which drastically cuts their energy needs. This isn't some pie-in-the-sky technology. It's a practical, low-cost change that wineries can make today. It just goes to show you that sometimes the biggest sustainability wins are hidden in the smallest details.
And that leaves us with one final thought. If a simple little tweak to a century-old tradition can save this much energy for just one type of wine, well, it really makes you wonder, doesn't it? What other hidden efficiencies are just waiting to be discovered in all the other things we eat and drink every day?